Okay, starting with the redox reactions. Yes, uh, what are the redox reactions? If we would like to learn something about redox reactions, we need to know what is the oxidation state definition. Oxidation state could be treated in a huge simplification, of course, could be treated as a charge of the element after the total separation of the elements that create a compound. Yes, oxidation state of the element in the compound means, or oxidation state of the element in the compound is equal to the theoretical charge of this element after theoretical total separation of these elements from each other, uh, elements that creates a compound. So let's consider the oxidation state of potassium and chloride in potassium chloride compound. I would like to say to you one more thing, that oxidation state definition is derived from the another section of chemistry, I mean atomic structure, yes, and chemical bonds. I am talking about this in the another section, of course, section concerning this atomic structure. But here I would like to tell you this in brief, yes, and there's another section more deeply here briefly. Okay, so let's I think you know that if we dissolve potassium chloride, which is an ionic compound, dissolve in water, there is a dissociation process. I mean, this particle of potassium chloride dissociate into potassium cations and chloride anions. Yes. So between potassium and chlorine there is an ionic chemical bond. Yes. Let's write the scheme. Okay. After the total separation of these two elements, there is no break of this bond. Yes, this bond is composed of two electrons. One is from the chloride atom, and the second is from potassium atom. These electrons create a bond, so we have a pair of electrons. Yes, after total separation of potassium and chlorine, these two electrons are moved toward chlorine atom. Why? Because chlorine is more electronegative. It harder attracts electrons. So chlorine atom contains extra electron charge is equal to -1, and potassium atom lose this electron. Therefore, the charge of the chloride is equal to -1, and the charge of potassium is equal to +1. Let's sum these charges. +1 plus -1 give us 0. The potassium chloride is a neutral, considering of course the charge is a neutral particle. Yes, neutral particle net charge is equal to 0. Okay, so let's consider another example. Hydrochloric acid. In a hydrochloric acid, after dissolution in water, there is also dissociation. There is a creation of hydrogen cations and chloride anion. The same situation. Between hydrogen and chloride, there is no ionic bond, but polar covalent bond. The same situation. There is no breakage of this bond, but the pair moves toward more electronegative more electronegative atom. Yes, so the charge in water solution, the charge of the hydrogen is equal to plus 1, and the charge of the chloride ion is equal to minus 1. So we have chloride anions and hydrogen cations. Let's consider, so the oxidation state of the hydrogen in the chloride, in the hydrochloric acid, the oxidation state of hydrogen is equal to plus 1. The oxidation state of chlorine in this compound is equal to minus 1. The total is equal to 0. The net charge, the net oxidation state of hydrochloric acid, which is neutral particle, is equal to 0. Let's consider oxidation state of the sulfuric acid. So here we have a more complex, more difficult example. Okay, so after this solution sulfuric acid in the water, there is also a dissociation. The particle dissociate into two hydrogen cations and one sulfate anion. The charge of the sulfate anion is equal to minus 2. The charge of every single hydrogen cation is equal to plus 1. Two hydrogen cations give us charge equal to plus 2. Plus 2 plus minus 2 give us 0. So the net charge, net oxidation state of the sulfuric acid particle is equal to 0. Okay, so let's consider every single atom here in the sulfate anion. We need to consider in this situation structural formula of the particle of the sulfuric acid. So let's draw it. Okay, between hydrogen and oxygen there are polar covalent bonds. Between these atoms that you see, I mean these oxygen atoms and sulfur atom, there are also polar covalent bonds. But here we have a coordinate covalent bonds between sulfur atom and these two last oxygen atoms. Okay, so as I said to you previously, oxidation state is equal to charge of the element after the theoretical total separations between elements. So we need to find the most electronegative element. In this particle it is oxygen, then sulfur, and the last electronegative hydrogen. So after the total separation, oxygen gets this pair of electrons, this pair of electrons, this pair of electrons, and this pair of electrons. So you can see that every single hydrogen atom loses one electron. So we get 2H plus cations. Here sulfur loses one electron and second electron from these two oxygen atoms. But here we have a two coordinate covalent bonds. It means that here the pair of electrons is given only by the sulfur. So here these two electrons and these two electrons are taken by this and this oxygen atom. However, those two electrons and those two electrons are given previously by the sulfur atom. So we have two hydrogen cations, four oxygen anions with the oxidation state -2. Every single oxygen atom takes 2 electrons. And we have one sulfur atom which lose 1, 2, 3, 4, 5, 6 electrons which were taken by the oxygen atoms. So if the sulfur atom loses 6 electrons, its oxidation state is equal to +6. Let's sum it. 2 times 1 give us 2 plus. 4 times -2 give us -8. 2 plus -8 -6. 1 times +6 give us +6. -6 plus 6 give us 0. Okay, let's consider another type of particle which is not neutral particle, but it is an ion. Here we have an ion of permanganate. Okay, we have 4 oxygen atoms. 4 oxygen atoms. Every single oxidation state is equal to -2. In 99.9% of compounds, oxidation state is equal to -2. There are some exceptions, like the compounds with fluoride or peroxide or some oxides. But mostly oxidation state equal to -2. So these 4 atoms of oxygen give us the total oxidation state equal to -8. So if the net charge of this ion is equal to -9, oxygen gives us -8, so the oxidation state of manganese is equal to, yes, you are right, +7. Let's consider the oxidation state of the elements in the dichromate anion. You could see that the net oxidation state of this anion is equal to -2. We have 7 oxygen atoms, every single with the oxidation state equal to -2. It gives us -14. -14 from oxygen. The net charge should be equal to -2. So the chromium should give us +12. So every single chromium atom gives us +6 because we have 2 atoms of chromium. 2 atoms give us +12. So 1 plus 6. Okay, guys, let's go back to the redox reactions. Redox reactions are electrochemical reactions. The whole electrochemistry could be described by the 2 electrochemical reactions: reduction reaction and oxidation reaction. The word redox is derived from these 2 words, reduction and oxidation. Reduction reaction is the reaction of the decrease of the oxidation state. Yes, the decrease of the oxidation state of the element which stands alone or is a part of a neutral particle or an ion, complex ion or complex cation. Yes, so the reduction reaction is a decrease of the oxidation state. Oxidation reaction is an increase of the oxidation state of the element. Both of these reactions proceed always together. There is no situation that every of this reaction proceeds single. I mean, if there is a reduction reaction in the system, there always should be also oxidation reaction. They both proceed together always. Okay. The oxidation reaction is always called, could be always called anodic reaction. Reduction reaction is a cathodic reaction. Oxidation, once again, oxidation, increase of the oxidation state, reduction, decrease of the oxidation state. Let's see some examples of the oxidation reactions. Here you have the first example. Here you have a metallic iron. Yes, metallic iron atom or 1 mole of atoms. Metallic iron oxidation state, it will of course to 0. Iron in this situation, metallic, isn't in any compound. It stands alone in a metallic form. So you could see that there is a big increase of the oxidation state of the iron. There is a decrease of the charge. Yes, so there is a creation of cation of iron cation. This cation lose 2 moles of electrons. The same situation below. We have metallic alumina, oxidation reaction, so the increase of the oxidation state, increase of the charge, we obtain aluminum cation with the charge equal to +3, which lose 3 electrons. Another 2 examples, more complex, yes? This one, the third one. We have reaction. We have 2 atoms of metallic copper with the oxidation state equal to 0. So, on the right side of the arrow, so in the side describing the products, we have component containing copper here. It is a copper oxide. This oxide contains 2 atoms of copper. Every single copper atom in this compound oxidation state is +1. Okay. The oxidation state of the oxygen atom is equal to -2. The whole gives us net charge equal to 0 because 2 atoms of copper, which every single is equal to +1, give us +2. Okay, so 2 atoms of the metallic copper lose 2 electrons and we obtain 2 atoms of the copper on the +1 oxidation state. So on this page you have the scheme of the oxidation reaction of the metallic iron to the cation form. Yes, and as you can see, here we have a metallic bar of iron. Yes, here we have metallic bar of iron, and this iron is immersed in the electrolyte. And there is a oxidation reaction of iron. Yes, so the atom of iron lose left these 2 electrons here and pass to the electrolyte solution, cation. Okay, so let's now see some examples of reduction reaction. Yes, we have 3 examples. The first one, the reduction reaction of the 2 hydrogen cations. Yes, you could see that every single hydrogen cation oxidation state is equal to +1. We have 2 hydrogen cations which consume 2 electrons. So the oxidation state of every single cation, hydrogen cation, is diminished to oxidation state equal to 0, because here we have a particle of hydrogen. In the particle of hydrogen, every single hydrogen atom oxidation state is equal to 0. In the second example, there is a reduction reaction of the copper cations. Yes, copper cations consume 2 electrons, which give us metallic form of the copper. The third one reaction, you could see that the third one reaction is the reverse reaction of the oxidation of the metallic iron. Previously, I show you oxidation reaction of the iron. Yes, previously. So from metallic form to the electrons and cation form. Here we have a reverse reaction. Yes, from cation form to metallic form, and it is reduction reaction. Here you have a scheme of the reduction reaction. Yes, the excess of electrons which are taken by every single hydrogen. This is of course example of the reduction of the hydrogen ions. Yes, the excess of electrons we have, and every single cation of hydrogen consume every single electron, and there is a creation of the particle of the hydrogen. Yes, in this particle every single hydrogen atom oxidation state is equal to 0. As I said you previously, that those reactions cannot proceed alone. Yes, they are also accompanied. Oxidation reaction always proceeds together with the reduction reaction. Therefore, we could write an overall reaction. Let's see it on the examples of the oxidation of the iron and reduction of the hydrogen. Yes, anodic reaction, so it is oxidation reaction, and cathodic reaction, so reduction reaction. Okay, so let's divide all of these two, anodic and cathodic reactions, into substrates and products. We know that the substrates are on the left side of the arrow. Products are on the right side of the arrow. Yes? So on the left side we have metallic iron and 2 cations of hydrogen. So we are writing these 2 substances on the right side of the total whole reaction. On the right side, on the right side of the arrow, so in the side of the products, we have cation of the iron and the particle of the hydrogen. So we are writing it on the right side of the total reaction. Let's see about the electrons. how many electrons took part in this overall reactions? 2 and 2 means 4? No, no 4. The answer is 2. Let's see. These 2 electrons here, which are given by this cation from, or maybe it will be more proper to say that these 2 electrons are given by this metallic iron, and then creates cation is created, and these 2 electrons, and these 2 electrons are consumed here by the 2 cations of hydrogen, and there is a creation of the particle of hydrogen. So these electrons are these electrons, yes? So we could avoid writing electrons in the overall reaction. Let's see the scheme of this. Let's see the scheme of this whole overall reaction. We have a bar of the metallic iron, which is immersed in the electrolyte. Yes. So there is an oxidation of the iron which pass to the electrolyte. This iron atom leaves 2 electrons which are consumed one by 2 hydrogen cations. So there is a creation of the particle of hydrogen consists of 2 atoms of hydrogen, every single with oxidation state equal to 0. Okay, so this is the overall reaction, overall electrochemical reaction. So guys, let's get back now to the examples. Let's solve some example of the overall electrochemical reactions with oxidation reaction and reduction reaction.